In this video, we'll discuss another application of second order linear differential equation, which is modeling of RLC circuit with an AC source. So here we have RLC circuit and this driving voltage is an AC source whose voltage is given by E naught sine omega t. Now resistance is R, capacitance is C and inductance is L. Now using Kirchhoff's law, we can write voltage drop across inductance, which is L di by dt, plus voltage drop across capacitor, which is Q by C, plus voltage drop across resistor, which is IR, and it will be equal to E naught sine omega t. We'll make it a second order differential equation in current, and for that we'll differentiate it again with respect to t. So now we can write L d square I upon dt square. We'll take this term. Now it will be this R di by dt plus, now dq upon dt is nothing but current I. So there will be I upon C, and this is E naught omega cos omega t. Now we'll divide everything with L, so we can write I double dash plus R by L I dash plus I upon LC, and it is equal to E naught omega cos omega t upon, which is a second order linear differential equation, but it is non-homogeneous. Now first we'll solve this homogeneous part. We'll find IH. So for IH we'll write I double dash plus R by L I dash plus I upon LC equals to 0. Now we can write its characteristic equation as lambda square plus R by L lambda plus 1 upon LC equals to 0. Now solving this quadratic equation, we can write lambda equals minus R by L plus minus under root of R by L whole square minus 4 upon LC divided by 2, or we can simply write this as lambda equals minus R upon 2L plus minus under root of R upon 2L whole square minus 1 upon LC. Now for the sake of brevity, what we'll do is we'll let alpha as R upon 2L, and we'll take 1 upon LC as some omega naught square. We can write this lambda as minus alpha plus minus under root of alpha square minus omega naught square. Now depending on the discriminant of this quadratic equation, we'll have three separate cases. So our first case is case of overdamping. Now in case of overdamping, this D, it should be greater than 0, and if D is greater than 0, that means alpha should be greater than omega naught, that is R upon 2L should be greater than under root of LC, or R should be greater than 2 times under root L by C. Now when we have this condition, we know our basis will be e to the power minus, we'll take minus common, alpha minus under root of alpha minus omega naught square t, and y2 will be e to the power minus alpha plus under root of alpha square minus omega naught square t. So basically we'll have our IH as a function of t will be C1 e to the power minus alpha minus under root of alpha minus omega naught square into t plus C2 into e to the power minus alpha plus under root of alpha square minus omega naught square into t. And we know that for x greater than 0, e to the power minus x, it decreases very rapidly. So this transient current will soon become 0 without any oscillations. So basically this circuit is said to be overdamped because two superimposed exponentials, they are both driving the current to 0. And it'll happen when the resistance is high relative to the resonant frequency. So overdamped response of this RLC circuit is a decay of transient current without oscillation. Now we'll come to the second case, which is critical damping. Now in case of critical damping, D is basically 0, and if D is 0, that means this R, it is equal to 2 times under root L upon C, and in this case basically lambda 1 will be equal to lambda 2 and will be equal to minus alpha. So the transient response of critical damping will be IH equals C1 plus C2t e to the power minus alpha t. Now again here alpha is positive and we have this exponential function with a negative sign, so e to the power minus x will also decay exponentially. Now the response of critically damped circuit is similar to that of overdamping circuit, but here the decay is in the fastest possible time without going into oscillation. So in this case, this decay will happen faster and the system will reach the steady state quickly without going into oscillation. And now we'll come to the third and the most important case of a series RLC circuit, and which is underdamping. Now in this case, alpha square minus omega naught square will be less than 0. So the two roots, they'll be minus alpha plus minus iota under root of omega naught square minus alpha square. So basically we can write its transient response IH as e to the power minus alpha t into C1 cos under root of omega naught square minus alpha square t plus C2 sine under root of omega naught square minus alpha square t. Now here too we have this e to the power minus alpha t term, and suppose this is some omega 1, we can write e to the power minus alpha t, and here will be some a cos omega 1 t plus phi. This transient current will again reduce to 0 exponentially, but here we'll have damped oscillations. So in this case, the current will still go down to 0, but the current will undergo oscillations. So basically these underdamped response, it is a decaying oscillation at a frequency of omega 1. And these oscillations, they decay at the rate determined by this coefficient alpha, because boundary of these oscillations is set by e to the power minus alpha t. Now if we look at all the three cases, whether it is over damping or critical damping or under damping, this transient response of the circuit or IH, it quickly reduces to 0. In case of over damping and critical damping, it is going to reduce to 0 without oscillation, and in case of under damping, it will still reduce to 0, but it will have damped oscillations. So this is the transient response of the circuit, which is soon going to die off. So in the steady state, the response from the circuit we'll have is IP, and this is what you want to study. So we want to study steady state response. And for it, we need to find its particular solution. Now, in order to find its particular solution, we look at this Rx, and we know that if Rx is of the form K cos omega t, then the choice of IP is A cos omega t plus B sin omega t. Now this I dash P will be minus A omega sin omega t plus B omega cos omega t, and I double dash P will be minus omega square A cos omega t plus B sin omega t. Now we'll put these three in this equation to find the value of A and B. So if we compare coefficient of cos omega t, we can write minus omega square A plus this is B omega R by L, so it will be B R omega upon L and plus A upon LC cos omega t, A upon LC, and it will be equal to E naught omega by L. Now we'll divide everything with omega square, so we can write minus A plus B R upon omega L plus A omega square LC, and this is E naught omega L, or this A minus 1 plus 1 upon omega square LC plus BR upon omega L, and this is E naught omega L. Now we know that omega L is nothing but it is XL, which is inductive reactance, and 1 upon omega C, it is nothing but it is capacitive reactance XC. So we can write this equation as A minus 1 plus, and this is XC upon XL plus BR upon XL, and is equal to E naught upon XL, or we can write A XC minus XL plus BR, and it is equal to E naught. And that's our first equation. If we compare terms of sign, so we'll have minus B omega square, and then R by L, A omega, so it'll be minus R by L, A omega, and then B by LC, and it'll be equal to 0. Now we can write this as minus b minus AR upon omega L plus b upon omega square LC, and it is equal to 0. We'll take terms of b together. So it will be this minus 1 plus, and this is XC upon XL, and this is minus AR upon XL equals to 0. So we'll get this as minus AR plus B XC minus XL, and this is equal to 0. Now from here we can write B into XC minus XL minus AR equals 0. And we also know that XL minus XC, it is S, and we call it as reactance. So we can write these two equations as minus AS plus BR is equal to E naught, and here will be minus BS minus AR, and that will be equal to 0, or we can write B equals minus AR upon S. So if we put it here, we can write minus AS minus AR square upon S, and that will be equal to E naught. Basically this A will be minus E naught S upon R square plus S square. Now B is minus AR by S, so this S will cancel. So this B will be E naught R by R square plus S square. So now we have the values of A and B. So we have AS minus E naught S upon R square plus S square, and this BS E naught R upon R square plus S square, where S is XL minus XC, or basically it is omega L minus 1 upon omega C. Now we can write this particular solution as A cos omega t and B sin omega t, and here we will take E naught R square plus S square common, and then it will be minus S cos omega t plus R sin omega t. We can also write this as E naught upon under root of R square plus S square, and this is sin omega t R upon under root of R square plus S square minus cos omega t S upon under root of R square plus S square. Now if we take this as cos delta and this as sin delta, we can write this IPS E naught upon under root of R square plus S square, and this is sin omega t minus delta, or we can write this IPS E naught upon under root of R square plus, and this is omega L minus 1 upon omega C square sin omega t minus delta, where delta is tan inverse S by R, which is tan inverse omega L minus 1 upon omega C by R. So this is the particular solution to this RLC circuit differential equation. And in this quantity and this quantity under root of R square plus omega L minus 1 upon omega C whole square, it is called as impedance. So once we have IP and IH, we can write I as a function of TS, IH plus IP. Now this is transient response of the circuit, and after some time it goes to 0. So in the steady state, the current in the circuit as a function of time will be given by this IP, which is E naught upon under root of R square plus omega L minus 1 upon omega C whole square sine omega t minus delta. After some time, the output will practically be a harmonic oscillation whose frequency is same as the frequency of input voltage. And here we also talk about something called as natural frequency of the circuit. So if we want this current to be maximum, this impedance, it should be minimum. Now the minimum value of impedance will be when the terms within this square root, they are minimum. Now if R is unequal to 0, then the only condition we'll have here is omega L minus omega C equals to 0. From here we'll write this omega square equals 1 upon LC. So natural frequency or the resonant frequency of this circuit will be omega naught, and that will be equal to 1 upon under root LC, and at that frequency this current will have maximum amplitude. Now let us take one example. Here we are given a series RLC circuit where R is 8 ohm, C is 0.1 farad, L is 2 Henry, and it is connected to an AC source whose voltage is given by 160 cos 5t. Now in this question we need to find steady state current. All we need to do is we need to find its particular solution. But what we'll do is we'll find its transient solution, that is solution to its homogeneous part as well as its particular solution. Now first we'll write differential equation of the problem. Now we know that L di by dt plus IR plus Q by C, and that will be equal to 160 cos 5t. Now we differentiate this, we let L d square I by dt square plus R di by dt plus I upon C, and there will be 800 minus sine 5t. Now L is 2, so it will be 2 I double dash, R is 8, so it is 8 I dash. Now C is 0.1, so there will be 10 I, and this is minus 800 sine 5t. Now we can cancel everything with 2, so it will be I double dash plus 4 I dash plus 5 I, and this is equal to minus 400 sine 5t. Now first we'll find solution to this homogeneous part. So its characteristic equation will be lambda square plus 4 lambda plus 5 equals to 0, or lambda plus 2 whole square plus 1 equals to 0, that is value of lambda is minus 2 plus or minus iota. Now here alpha is minus 2 and beta is 1, so we can simply write this IHT will be e to the power minus 2t c1 cos x plus c2 sin x. So that's the solution of this homogeneous part. Now we'll find its particular solution. Now here this Rx, it is of the form k sin omega t, and if Rx is of the form k sin omega t, we can write its particular integral IPS a sin 5t plus b cos 5t. Now we need to find the value of a and b. For this, what we'll do is we'll find I dash p. So there'll be 5a cos 5t minus 5b sin 5t, and we'll find I double dash p will be minus 25a sin 5t minus 25b cos 5t. Now we'll put the value of IP, I dash p and I double dash p in this equation. What we are going to do is we're going to write terms of cos together. So we can write cos 5t. Now this is minus 25b. This is 4 plus 20a plus 5b, and then we write terms of sin 5t will be minus 25a, and then will be minus 20b plus 5a, and this is equal to minus 400 sin 5t. Now we compare cos. From here we'll get a equals b, and if we compare sin, we'll get minus 20 a plus b will be equal to minus 400. So a plus b is 20, and since a and b they are equal, so value of a and b, they are 10. So it simply means that its particular solution will be 10 sin 5t plus cos 5t. Now we can write its solution ITS IH plus IP. So it will be this plus 10 sin 5t plus cos 5t. Now what it is asking for is steady state response, and for steady state response we'll take this limit t tends to infinite. So in this case this I will be, now e to the power minus infinite is 0, so this entire term will be 0. So its steady state current will be 10 sin 5t plus cos 5t, and that is the answer to this question.